What is a distortion-less communication channel? The title may sound a little bit complicated, but as we will see, it's quite simple in fact. So before we talk about the distortion-less communication channel, let us first have a look at the perfect communication channel. So basically what a channel is basically something that connects the receiver to the transmitter to the receiver. So it might be a coaxial cable, it might be even a free space, a pair of wire, whatever thing that can transmit the signal, that we can transmit the signal through. So ideally we want the input that is coming from the transmitter to be equal to the output. We don't want this channel to act to our system. We don't want it to do anything basically. We just want to connect the transmitter to the receiver. So we call this a perfect communication channel. When the output is equal to the input, this is a perfect condition, a perfect state. So actually such a channel cannot exist basically because of the losses in the channel. Any channel it has to have some losses, even in order of it depends on the frequency and other factors, but it has to have some loss. So it can't be 100% accurate, because if you even a pair of wire, it has some resistance and there is a voltage drop across the resistor, and it will have some loss in it. Even the free space, if you take the free space, the radiation goes in all directions, and there will be some power lost. You won't receive the all the radiation that you have transmitted. So actually there must be some loss in the channel. So a more practical term, or a more accurate term, is the distortion-less communication channel, in which let's say this is the input as a function of time. Let's call it x of t. So if the input has some goes up a bit and it goes down to 0, so if let's say that's the input to the channel, to the distortion-less communication channel, the output will be, on the other hand, it's function of time. Let's call it y of t instead of x. So y of t will have some time delay, because any signal, the channel cannot, the signal cannot pass through that channel faster than the speed of light. So it has to have some time delay, where some propagation delay actually through the channel. So it will start, instead of starting from here from 0, it will start from TD, and we call this a time delay. And then it goes up just like the other one. It's basically the same shape, but it's attenuated a bit, because as we have explained, the channel has to have some losses, and any medium can have some losses. So if this is, let's say this peak is 3 volts, for example, there's gonna be maybe 2.5 volt or something like this, because the channel has some attenuation constant. And if this point, let's say this is 1, there's gonna be the same factor. It's gonna be 1 multiplied by 2.5 over 3, So actually it will be attenuated by the same factor over all the points. So every point will be multiplied by an attenuation factor A, which is constant along the time domain, along the whole signal. So actually, let's write this mathematically. We would say this is a channel. Actually, any channel has some, any system, linear time invariant system, any system has some unit impulse response. We call this h of t. And our channel has an input, which is x of t, this input. And then the output for a distortion-less communication channel is going to be the same as the input, but it has some it gets multiplied by some factor A, which is going to be less than 1. It's an attenuation factor, so it's going to be the same signal, but it's also delayed in time td, so that when t is 0, see here, look up here, when t is 0, we get here td, t equals td in the output. So so here when the with the same value comes when t equals td instead of t equals 0, and same for t equals 1 comes when t equals td plus 1, and so forth. So we want to know what h of t is in order to meet our specifications for a distortion-less communication channel. So we know that in any linear time invariant system, the input, when it gets convolved with the unit impulse response, is gonna give us the output, which is in our case is the with this expression up here. So this is the equation that we have to solve. We have to solve for h of t. So actually we can do this in time domain, but it's gonna be quite complicated because you have to work an integral. You know, there is an integral here for, between x and h of t, so you have to do some integral equation and something like this. But to ease things off, we will apply a Fourier transform to both sides of the equation. So the Fourier transform is a linear operator. Actually, before we talk about this, the Fourier transform, when it gets applied to convolution, it becomes multiplication in the frequency domain. So that's the advantage actually of the Fourier transform, and that's why we have applied it to our system. So and here on the other hand, the Fourier transform is a linear transform. So the constant we can get the constant as a common factor out of the transform, and we can have it right here. And then we have the Fourier transform of a delayed version of x of t. The Fourier transform of x of t minus td. Actually, if we use the Fourier transform properties, we will find that this is the same, basically the same as x of the Fourier transform of x of t, which we call x of f, but it gets multiplied by a factor, a phase angle, which is e to the negative j 2 pi tdf. So we just write this down, x of f times e to the negative j 2 pi tdf. So we can cancel out x of f with x of f, and we'll be left with h of f that we want. So this is going to be a times e to the negative j 2 pi t sub df. So this function, this is basically the transfer function of our channel. So it has some amplitude of a, and it also has some phase. It has some phase shift of negative 2 pi t df. So what we can observe from this is that the a is basically a constant. You know, a is the attenuation constant, so it doesn't change. So this means that the first condition for the channel to be distortionless is that the transfer function amplitude or magnitude is constant. And the second criterion is, or the second condition is that the phase is basically a constant, a negative constant, and it's multiplied by the frequency, which is varying. So that means the phase is linearly proportional to the frequency, because we can abstract this by k. So this is just k times f. So the second criterion is transfer function phase is linearly proportional to frequency, and we can also add it's gonna be a negative slope. So these are the conditions that have to be met in order to have a distortionless communication channel. Actually, we have derived how we obtain these two conditions mathematically, but maybe we still don't have an intuitive understanding of why this is so. Why do we have to have a communication channel which has a transfer function magnitude is constant, and the phase of the transfer function has to be linearly proportional to the frequency with a negative slope? Why do we have this actually? So actually, let's take the first condition and see what it implies. So the first condition, it says the magnitude has to be held constant. So let's say the magnitude is a function of the frequency, is some constant a. So what this means is that it responds to the different frequencies. It responds to all of them equally. So let's say we have a signal. This is x of f, and let's say something like this, like that, and then goes back like this, any arbitrarily shape actually. So this function has some low frequency components. This is in time domain is gonna be a sine wave like this. Here we have a little bit higher frequency, maybe like this. Here we can have a very high frequency, which is maybe like this, something like that. So the transfer function is gonna be multiplied by all of these, by x of t. So it's gonna be multiplied by this frequency and that frequency and this frequency, all of them. So if h of f is varying, if the magnitude is varying with frequency, that means it's gonna deal with this frequency. Maybe it's gonna amplify this frequency component, and it's gonna maybe attenuate this frequency component. Is gonna have some distortion in the frequency spectrum. So if it's just multiplied by a constant, this is not gonna affect the shape or the frequency distribution in the transfer from in the input. So the output is gonna be just the same shape as the input, but it's let's say this is the output. So the output is gonna be the same shape, but maybe it's a bit less than the input. So this is what is gonna happen. So that's a distortion, let's say, a non-distorted signal. Because it's not distorted, it's the same shape in the frequency domain. It's gonna be the same shape in the time domain as well. So this is the first condition, and we understand intuitively why this is the case. So what about the second condition? The second condition actually looks a little bit weird, because at first when I have studied this, I thought the phase has to be constant as well, so we will have a constant time delay, but actually it turns out this is not the case. Actually, for the second condition, we can demonstrate this by writing down the equation for a sine wave. If we have a sine wave with some phase shift, let's call phi. So this is our output signal. This is y of t. So if this phase shift, and let's say we have some multiple of these sine waves from n, from 0 to maybe m, and this is sine sub n. Actually, this is a discrete time, a discrete Fourier transform, but actually is basically the same idea. If we talk an infinite number of these sine waves, it's basically the same idea. So the idea that I want to demonstrate is that if the phase shift is linearly dependent on the frequency, so it's k omega, this is gonna be omega t plus k omega, and we can take the omega as a common factor, and we will be left with t plus k times omega. So as you can see, if k is a negative number, this is gonna be, let's say, k equals negative td. So this is gonna be sine of t minus td times some frequency omega. So what is this basically means is just a time shift. But if the if the frequency is proportional to the if the phase is proportional to the frequency, this is gonna happen. If the phase is constant, that means there will be some dependence on the frequency in the signal, in the time delay. So the time delay itself will be dependent on the frequency, and there will be some distortion. So I hope you understood this. It's a little bit, it needs time, so you can repeat this part of the video to get to understand it. Actually, if this phase is a constant, you will have, maybe this is gonna work and this is gonna help. If we took a signal as just a sine wave like this, and we took another signal which has some higher frequency, so if we sum them up, so what is gonna happen? Let's say we have the input will be the summation of these two signals. If the output, if the phase of the output is constant, that means the first signal will be shifted with, let's say the phase is just pi over 2, whatever, any constant. So the first signal will be like this. The second signal will be like this. So as you can see, this signal goes down to 0 faster than this signal. So it doesn't, at this point, this starts at 0, the other one is still not at 0 as it was here. So there will be some distortion due to this. They don't start from the same point. But if we took the phase as a function of the frequency, and we said pi over 2 times omega of this frequency, let's say omega here is 1, so it will be pi over 2 of omega here is bigger than 1, so it's the frequency is higher, it will be, they will meet at the same point, and then the frequency will continue. So there will be some time shift, but in a constant phase, there will be some distortion. So hopefully we have explained intuitively why the first condition has to be met and why the second condition has to be met. So the question that remains in mind is how to verify this in a real system. So let's say we have a channel and we want to test it. We don't know whether it's a distortion-less or maybe it's distorted or noisy. We don't know what the response is going to be. We don't know h of t or h of f. We don't know this function basically. How can we tell whether this is a distorted channel or maybe it's distortionless? So actually what we do in practice is that we apply different frequencies. Maybe we'll apply some function sine of omega t. So for omega is equal to 1, there will be some output. So we will record this first output when omega is equal to 1, and we'll see the response. We'll see the amplitude and the phase, and we can plot, for different frequencies. For different frequencies, what is gonna be the output over the input? Let's call V out as the voltage output, and over Vn as the voltage input in the frequency domain. So this is gonna be the h of f. So we take the output signal and we divide this by the input, and we'll have some curve. So actually I can show you a real circuit which does so in practice. In practice, you would have a computer or a microcontroller, whatever, it's something that you can program. So you write a program in it. So maybe the program starts from, it has a loop in it from zero frequency and it jumps every 1 kilo hertz, and then goes to 100,000 kilohertz, which is 1 megahertz. So maybe it is arbitrary. Actually, you can do it as whatever you want. You're the programmer. So the computer then goes to actually the computer can't get it can't generate a sinusoidal signal, because that's a digital computer. It only deals with ones and zeros and stuff like this. So we can only generate a pulse width modulated signal. So something like you have pulse width modulated signal is a signal where you can you have a small period of time high, then a low period, then maybe a high period, stuff like this. So actually, in a pulse width modulated signal, you vary the duty cycle. So you vary the duty cycle, and you can get different average voltage for different frequencies. So actually, what you do is you're encoding the voltage. Instead of it changing the voltage sinusoidally, you can encode the output voltage in that pulse width modulator, and then you can apply a low pass filter. Normally, this pulse width modulated signal is in the order of maybe some hundreds of kilohertz. So actually, this signal is quite high frequency, relatively high frequency. When it passes through a low pass filter, actually the signal gets smoothed out, and you get the average signal. So what you do is you have a constant voltage, which is equal to the VCC, or the 5 volts, multiplied by the duty cycle. So that's what you have as an output. Is the let's call it Vn, because it's gonna be Vn. So what you have is, then you have a voltage controlled oscillator. So the voltage controlled oscillator has some, it responds for a given input. If the input voltage may be 3 volts, it will have some frequency in response to this 3 volts. If you increase the voltage to maybe 5 volts, it will have a output frequency, the output frequency will increase linearly with the input voltage. So we say that the frequency is proportional to the input voltage. So this is what we will get out of the voltage controlled oscillator. We'll get a sine wave with 2 pi f t. So f is basically dependent on the Vn, which is dependent on the pulse width modulated signal, which is dependent on the programs that you're running. So actually, this is how we do this in practice. So actually, after generating the signal, you just pass it through the channel, and then the channel will have a response to the signal, and you can give it right back to the computer, and the computer will display the output signal. So normally, for a real system or a real channel, you'd have a curve which looks kind of like this. Is the frequency, and this is the magnitude of h of f. So basically, for a distortionless channel, we want this voltage to be, we want this magnitude to be constant like this. But for any real system, for any real any real system, any real channel, you'd have something like this, a curve which looks like this and then goes down like this. So actually what this looks like is that it favors these frequencies, this small band of the frequencies, and it gives them some more gain than the other frequencies. If you send some signals over this frequency band, for example, it will be distorted, it will be attenuated, it will be, it's not gonna be a good thing to do. So we call this the channel bandwidth, the bandwidth in which the frequency response is going to be a constant, and the phase response is going to be linearly dependent, linearly proportional to the frequency. So we call this the bandwidth. So this is the definition of the bandwidth of a given channel in practice. So actually the bandwidth is very